Okay, let's unpack this. Imagine for a moment, draining all the water from our oceans. What would you expect to see? Just a colossal, flat bathtub bottom.
Probably, yeah. Or maybe some bumps.
Right. Or maybe something far more diverse and dynamic, revealing these um, colossal forces at play. For most of human history, that vast, watery expanse was a complete mystery.
Totally unknown.
But as it turns out, the ocean floor is anything but boring.
Mm.
This deep dive is all about uncovering the hidden topography and, well, the immense geological processes shaping the Earth's most prominent feature, covering over 70% of its surface.
It's huge.
We're going to reveal how the ocean floor forms, evolves, and is ultimately recycled, giving you a shortcut to understanding one of our planet's greatest stories.
And what's truly astonishing here is how recently we've even begun to piece this story together. It wasn't until, the 1950s that modern instruments truly allowed us to peer beneath the waves.
Really that recent?
No.
Wow.
Yeah. Discoveries like the global oceanic ridge system. I mean, a submerged mountain range longer than any on land completely reshaped our understanding of Earth's dynamics.
Right.
So our mission today is to take you on a journey, piece by piece, through these immense unseen landscapes, helping you visualize the constant creation and destruction of our ocean floor.
So if this underwater world was a mystery for so long, the first fundamental question is, how do we even know what it looks like? How do we map something we can't see?
Good question.
This is where the science of bathymetry comes in, literally. The measurement of ocean depths and the charting of the seafloor's topography. Early efforts, like the pioneering HMS Challenger expedition back in the late 1800s.
Painstaking work.
Oh, incredibly slow, lowering weighted lines point by point to measure depths. That's how they famously revealed the astonishing 10,994-meter Challenger deep.
Imagine doing that. But those early efforts, while monumental, modern technology has just revolutionized our ability to map the deep. The first big leap came with sonar sound navigation and ranging.
Like bats or dolphins.
Sort of, yeah. Basically, an echo sounder sends out a ping of sound, and by timing how long it takes for the echo to return from the seafloor, we can calculate the depth. Think of it like shouting into a canyon and waiting for the echo.
Simple enough in principle.
Right. And then more advanced sonar, like multibeam instruments mounted on ship hulls, they send out a whole fan of sound that covers wide swaths of the ocean floor.
Half mile more efficient.
Much more. It collects incredibly detailed, high-resolution bathymetric data, allowing us to build these, precise 3D maps.
And here's where it gets truly mind-bending. We can even map the seafloor from space.
Without even getting wet.
Exactly.
Yeah.
Satellites orbiting Earth can tell us about the deep ocean without ever seeing it. They use radar altimeters to measure incredibly subtle variations in sea level. We're talking just a few centimeters.
Tiny variations.
Tiny. But these tiny bulges or depressions on the ocean surface are caused by the gravitational attraction of massive features on the seafloor below. A huge underwater mountain, for instance, it pulls water towards it, creating a slight hump on the surface.
Gravity's effect on the water itself.
Precisely. So by precisely mapping the ocean's surface, we can infer the hidden topography below.
It's an ingenious way to fill in the blanks, especially for areas where ships haven't yet surveyed. And from all these mapping efforts, oceanographers have identified 3 major topographic provinces of the ocean floor: the continental margins, the deep ocean basins, and the oceanic ridges.
Okay, 3 big zones.
Each tells a different story about our planet.
Let's start where land meets sea then, with the continental margins, those submerged outer edges of our continents. They're divided into 2 main types, and the difference, you said, is all about plate tectonics.
Exactly. Passive continental margins are, geologically quiet. They're far from active plate boundaries, so you won't find major earthquakes or volcanoes there.
Okay, like the east coast of the U.S.
Perfect example. Think of the Atlantic Ocean, mostly bordered by these stable margins. They typically feature a gently sloping continental shelf, which is essentially a submerged extension of the continent.
Where we fish and find oil.
Right. Rich in resources, critical fishing grounds. Then there's a steeper continental slope, marking the true edge of the continent. And finally, a more gradual continental rise at its base, built up from thick layers of sediment washed down from the land.
So shelf, slope, rise. Got it.
But then, in stark contrast, you have active continental margins. These are dynamic. They're located along convergent plate boundaries, where oceanic lithosphere is actively diving or subducting beneath a continent.
Like the Pacific coast. Ring of fire stuff.
Exactly. Most of the Pacific Rim, like the western coast of South America, is lined with these. Here, the major feature is usually a deep ocean trench. As the plates grind past each other, sediment and pieces of oceanic crust can either be scraped off and piled onto the overriding continent.
Like snowplowing sediment.
Yeah, forming an accretionary wedge. Or, in some cases, surprisingly, it gets pulled down into the mantle in a process called subduction erosion. It's a much more dramatic landscape shaped by collision.
Wow. Okay, so from these dynamic edges, let's journey further out into the vast, deep ocean basins. This is, what, nearly 30% of Earth's surface? A truly abyssal, hidden world.
Indeed, and this realm holds some incredible features. Those deep ocean trenches we mentioned. They're the deepest parts of the ocean floor, often stretching for thousands of kilometers and plunging
Yeah.
over 10 kilometers deep.
Challenger deep territory.
Exactly. They are the battlegrounds where oceanic lithosphere dives back into the mantle, triggering powerful earthquakes and volcanic activity along parallel volcanic island arcs or continental volcanic arcs.
And slithering of fire.
That's why. Then you have the abyssal plains, which are incredibly flat. We're talking vast, almost featureless expanses.
Flatter than Kansas.
Probably. Often formed where thick layers of fine sediment carried out by underwater currents called turbidity currents bury the rugged ocean floor. It's actually fascinating that the Atlantic has more extensive abyssal plains than the Pacific.
Oh, why is that?
Well, it's mainly because the Pacific has so many deep trenches that act like giant sediment traps, preventing those sediments from spreading out across the basin floor. The Atlantic doesn't have as many trenches blocking the way.
Ah, interesting plumbing difference.
You could say that. We also find numerous volcanic structures out here. Seamounts are basically underwater volcanoes rising hundreds of meters from the seafloor. They're especially common in the Pacific.
And if they poke out?
If they grow tall enough to break the surface, they become volcanic islands. And sometimes these volcanic islands, after being eroded flat by waves at the surface, then gradually sink back beneath the waves as the tectonic plate moves away from its volcanic source or hotspot. They form these flat-topped submerged structures we call guyots.
Guyots. Okay, flat-topped seamounts.
Mm.
Got it. That's incredible. So much activity in these unseen depths. And speaking of volcanic islands sinking, it brings us to a beautiful paradox. Those ring-shaped coral reefs called atolls.
Ah, yes, atoll.
Corals need warm, shallow, sunlit water, right? But atolls often rise from astonishing depths. How do these massive living structures form?
This is where Charles Darwin's early observations, way back during his voyage on the HMS Beagle, perfectly align with modern plate tectonics.
Darwin again. Amazing.
He hypothesized that many volcanic islands gradually sink. As they sink, the corals, needing sunlight, continually grow upward, kind of keeping pace, building the reef structure closer to the surface.
So they're building on a sinking foundation.
Precisely. Plate tectonics provides the mechanism. Volcanic islands often form over these relatively stationary mantle plumes or hotspots. But as the oceanic plate moves, it carries the volcanic island away from its magma source. The lithosphere underneath cools, contracts, becomes denser, and slowly sinks over millions of years.
Allowing the coral to build upward.
Exactly, building upwards and outwards, forming those massive ring-shaped atolls we see today. It's a beautiful interplay of geology and biology.
So we've talked about deep trenches, flat plains, even sinking volcanic islands crowned with coral. But there's an even more massive feature crisscrossing the globe, the oceanic ridge system.
Oh, yeah, the big one.
It's the longest topographic feature on Earth, winding through all major oceans for over 70,000 kilometers. That's enormous.
It is. This immense system, typically standing 2 to 3 kilometers higher than the adjacent deep ocean basins, marks the plate boundary where new oceanic crust is continuously created.
The birthplace of the ocean floor.
That's right. While often called mid-ocean ridges, like the Mid-Atlantic Ridge, many segments, such as the East Pacific Rise, aren't actually in the middle of an ocean. And they aren't narrow peaks, but broad, elevated swells, sometimes thousands of kilometers wide.
How do they form then, if not by smashing plates together like mountains on land?
Good point. They're formed not by compression, but by the upwelling of hot mantle rock. This generates new basaltic crust that is hotter, less dense, and therefore buoyantly uplifted. Along the axis of slower spreading ridges, you'll often find these deep, down-faulted structures called rift valleys, like a colossal canyon running right down the center.
So it's primarily a thermal effect then. The heat makes it buoyant. Because my initial thought might be that new rock would just sink. Is the buoyant force of that heat really that strong, or are there other factors at play?
It is primarily the heat. You
Yeah.
got it. Newly created oceanic lithosphere is hot and therefore less dense than the cooler rocks around it. As it moves away from the ridge crest, this is the process of seafloor spreading. It gradually cools and contracts.
Ah, so it gets denser as it cools.
Exactly. It becomes denser and subsides to greater depths. That's why the ocean floor is generally deeper, further away from the ridge. The speed of this spreading also dramatically shapes the ridge itself.
How so?
Well, slow spreading rates, like you see in the Atlantic, maybe 1 to 5 centimeters per year, they create those prominent rift valleys and a very rugged, fractured topography. There's more time for faulting relative to volcanism.
Right?
But fast spreading rates, like much of the East Pacific, pushing maybe 9 centimeters per year or more, they produce a much smoother, broad central swell. It's built up by more voluminous lava flows, and there's often little or no central rift valley.
Fascinating how the speed changes the whole landscape.
Yeah.
Okay, we know the seafloor is being created at these ridges, but what exactly is it made of? What are these new slivers of seafloor actually composed of?
Right, good question. At its core, oceanic crust is typically about 7 kilometers thick and made of mafic rocks, meaning they're rich in magnesium and iron, primarily basalt and its coarse-grained equivalent, gabbro.
Basalt, like Hawaiian lava flows.
Very similar, yes. But the incredible insight here isn't just what it is, but that this consistent, layered structure provides us with a blueprint for how the ocean floor is built. The most distinctive feature you see right at the surface of newly formed oceanic crust are pillow lavas.
Pillow lavas, like soft pillows.
Huh. Not soft, but shaped like them. Imagine molten basalt erupting underwater. It gets rapidly chilled by the cold seawater, and it extrudes, well, kind of like toothpaste, from a tightly squeezed tube into these bulbous, pillow-shaped masses.
Okay, I can picture that. Toothpaste lava pillows.
Below these lavas are deeper layers. The salt that solidified in vertical cracks forming sheeted dikes, basically the plumbing system, and then even deeper, coarser-grained rocks called gabbro, which represent the slowly cooled magma chambers beneath the ridge.
A whole layered structure created right there.
Instantly, geologically speaking.
And what's truly astonishing is how the ocean itself plays an active role in transforming this new crust. It's not just sitting there.
Absolutely. That interaction is crucial. It creates something called hydrothermal metamorphism. Cold seawater seeps down deep into the fractured oceanic crust.
Through all those cracks.
Exactly. It gets heated to hundreds of degrees Celsius by the underlying magma and becomes chemically active. This hot, acidic water reacts with the basalt, dissolving minerals like silica, iron, copper, even sometimes silver and gold.
So it becomes like a mineral
A
soup.
very hot mineral soup.
Yeah.
And these superheated mineral-rich fluids then gush back out onto the seafloor at hydrothermal vents, creating these towering chimneys we call black smokers.
Why black smokers?
Because when these incredibly hot fluids hit the cold, deep seawater, the dissolved minerals instantly precipitate out as fine particles, forming these dark, smoke-like plumes. They build up massive metallic sulfide deposits around the vents.
Wow, and these aren't just geological curiosities, right?
Not at all. These vents aren't just geological wonders. They support unique ecosystems thriving entirely without sunlight. They rely on chemosynthesis bacteria using the chemicals from the vents for energy, forming the base of a food web with incredible creatures like giant tube worms and strange crabs.
Life finding a way in total darkness and intense heat. Amazing. So we've seen how the seafloor grows, changes, what it's made of, but where do entire oceans come from? How does a continent literally split in half to create a new ocean basin?
Yeah, the ultimate origin story. This is the dramatic process of continental rifting. It typically begins with continental rift formation. Picture a continent starting to stretch and thin.
Like pulling taffy?
Sort of, yeah. This is often initiated by rising mantle plumes, blobs of extra hot rock from deep within the earth that heat and uplift the overlying lithosphere, weakening it. This causes the upper crust to crack and break along faults, forming these downdropped blocks and valleys.
Like the East African Rift Valley.
Exactly like the modern-day East African Rift. That's stage 1. If this rifting continues, it can progress to stage 2, a narrow linear sea. Think of the present-day Red Sea. The Rift Valley has deepened, stretched all the way to the edge of the continent, and seawater has flooded in. You actually see seafloor spreading starting there.
A baby ocean.
Essentially, yes. Then finally, with continued spreading over millions of years, it matures into stage 3. A full-blown ocean basin, like the Atlantic Ocean today, complete with its own elevated oceanic ridge in the middle.
And the edges become
Those rifted continental margins, as they move away from the spreading center, they cool, sink, and get buried by thick layers of sediment, forming those stable, passive continental margins we talked about earlier.
The whole cycle, that's a massive process.
Mhm.
What are the primary driving forces behind this immense continental breakup? Is it just those plumes?
Well, the plumes are certainly a major factor. The broader context is often the supercontinent cycle, where continents periodically assemble into huge landmasses like Pangaea about 200 million years ago and then break apart again. Mantle plumes, they definitely play a significant role.
How so?
These columns of hotter than normal rock rise spread out beneath the continent, causing it to dome upwards and weaken, which helps initiate the rifting. Sometimes a single plume can even produce three rifts radiating outwards, forming a triple junction.
Arms.
Yeah. Often, two of those arms will develop successfully into an ocean basin, while the third one kind of stalls out and becomes a failed rift that doesn't fully open.
Any other forces?
Yes, absolutely. Tensional stresses from plate motions themselves are also key. If a continent is attached to an oceanic plate that's being pulled downwards into a subduction zone elsewhere, that pulling force can literally stretch and break the continent apart, often along pre-existing zones of weakness.
Makes sense. Okay, so since Earth's surface isn't actually getting bigger, despite all this new seafloor being made at the ridges,
Yeah.
all that new lithosphere has to go somewhere, right?
Exactly. Conservation of surface area.
How does this amazing cycle complete itself? How is the ocean floor eventually destroyed?
It's all about subduction. This is where older oceanic lithosphere descends, or sinks, back down into the Earth's mantle. It typically takes about 15 million years or so for new oceanic lithosphere to cool enough and become denser than the underlying warmer mantle, the asthenosphere.
So it gets heavy enough to sink.
Essentially, yes. And it's actually the dense, cooled lithospheric mantle part, not just the thin crust on top, that primarily drives the sinking process due to its increased density. We generally see two main styles or types of subduction zones.
Okay.
There's spontaneous subduction. This typically happens with very old, cold, dense oceanic lithosphere. It basically just sinks under its own weight quite steeply, pulling the plate down. This creates very deep trenches, like the Mariana Trench.
The plate just dives down.
Pretty much. Then you have forced subduction. This occurs when younger, hotter, and therefore less dense, more buoyant lithosphere is literally forced beneath an overriding plate by strong compressional forces between the colliding plates.
Like being pushed under.
Exactly. This results in shallower subduction angles, a tighter coupling between the two plates, and often leads to very strong earthquakes and significant mountain building on the overriding plate, like we see in the Peru-Chile Trench along the Andes Mountains.
Two very different ways for the ocean floor to meet its end. That's a stark reminder of Earth's dynamic nature. Can you give us a concrete example of an entire ocean basin being, well, consumed?
Oh, absolutely. History is littered with lost oceans. One of the best examples is the ancient Tethys Ocean. It used to separate Africa and Eurasia, but it was almost entirely consumed as those continents collided over millions of years. Only small remnants are left today, like the Eastern Mediterranean and the Black Sea.
Wow, an entire ocean gone.
Mostly gone, yeah. Another really fascinating case is the former Farallon Plate. This was a huge oceanic plate that once occupied much of the eastern Pacific Ocean off the west coast of North America,
Never heard of it.
because it's almost entirely gone now. As the Americas drifted westward, the Farallon Plate subducted beneath them much faster than it was being created at its own ridge, so it shrank dramatically.
What happened then?
Well, eventually this process was so immense that a section of the spreading ridge itself, the East Pacific Rise, actually got subducted beneath California. This collision and subduction of the ridge itself stopped normal subduction there and led to the development of a completely different type of plate boundary, the San Andreas Fault System, a transform fault.
So San Andreas exists because an ocean ridge died there.
In large part, yes. The Pacific Plate boundary essentially jumped inland and even captured parts of Southern California and Baja California, which are now slowly being carried northwestward along with the Pacific Plate as a result of this colossal geological reorganization.
Mind-blowing stuff.
So if we connect this all back to the bigger picture, you've journeyed with us from charting the invisible deep with satellites and sonar to understanding how entire continents literally break apart to form new oceans, and then how those old ocean floors are eventually recycled back down into the mantle. This entire process is just this constant, ongoing dance of creation and destruction. It's a real testament to the incredible forces at play beneath our feet, shaping everything we see.
Yeah.
We've seen how bathymetry reveals this hidden world, how passive and active margins shape our continental edges, the drama of the deep ocean trenches, those vast abyssal plains, and of course the immense oceanic ridges where new crust is born. We've learned about the unique pillow lavas, those fascinating black smokers supporting life in the dark, and the whole cycle of continental rifting and subduction that sculpts our planet over millions of years.
So what does this all mean for us? I mean, considering how much of the ocean floor is still unmapped,
Mhm.
you mentioned maybe only 5% in detail earlier, and how dramatically our understanding has evolved in just the last few decades. What other incredible secrets do you think the deep ocean still holds? Secrets about our planet's past, its present, maybe even its future. Perhaps there are even more surprising connections waiting to be discovered between the geology of the deep and the life it supports, or resources we haven't imagined.
That's the exciting part, isn't it? There's still so much to explore.
Thank you for diving deep with us on this incredible exploration of the ocean floor. We hope this deep dive has given you a shortcut to being well-informed and sparked even more curiosity about our amazing planet.